Now, another concept we have to hit is the idea of dielectric strength. This is not the same as the dielectric constant. Dielectric constant right over here, those are that's the factor by which the electric field within the capacitor decreases or the increase in the capacitance. That is not the dielectric strength. What I have on this table here is the dielectric strength over here in millions of volts per meter. The dielectric strength is simply the maximum electric field which a capacitor can endure without breaking down. When I say breaking down, I mean becoming a conductor. So basically, it's the limit of your field strength before this thing just starts conducting electricity. Now, it's supposed to be an insulator, but all insulators, if you have a strong enough electric field, will conduct electricity. For example, air. Now, a vacuum won't conduct electricity, but air, if you get the number here is 3, that means 3 million volts per meter. If the field strength is 3 million volts per meter, i.e. 3 million newtons per coulomb, air becomes a conductor and you get a spark. So your breakdown, in other words, when the capacitor actually just becomes a conductor, and if your capacitor is right here and this field gets strong enough in there, and this you don't want to happen, whoops, this is minus. If the field gets strong enough in there, boom, those charges can just jump across, and you have a spark, and you have generally a bad situation. So it's good to have a very high dielectric strength. And there's you can see a couple of these different values in there that different insulators have different dielectric strength. 3 million volts per meter or 3 million newtons per coulomb for air, then it becomes conductor. 60 million newtons per coulomb for Teflon, 14 million newtons per coulomb. Aluminum oxide has a very, very high dielectric strength, which means it's really hard to make it into a conductor. And that's 8 million volts per meter, 8 million newtons per coulomb. So dielectric strength is completely different than dielectric constant. It's basically how strong the field can be before you start actually becoming a conductor. Now, one specific style of capacitor that is very useful, but we got to be careful. We're going to use these in one of our labs. You got to watch out for these electrolytic capacitors. How they get the dielectric in there is just by creating a thin layer of corrosion between the plates through a chemical reaction that happens when you put electricity into the one side of this capacitor. It's got to come out the other side. But if you polarize it the wrong way, in other words, if you do not connect an electrolytic capacitor correctly, it will decorrode. The chemical reaction will reverse, and it will become a conductor. So how do you tell on this? Well, there's an easy way, the way to it's polarized. If you look on there right there, you will see there's a bunch of negative signs. And those negative signs are right next to this terminal of that thing, which means that that is the negative terminal. That is the one that you must connect to the negative terminal of your battery, or this thing will become a conductor. It will explode, and it could be dangerous. Usually it just goes pop, and it's kind of annoying or maybe a little bit frightening at first. But if you were in the wrong situation, if you were like looking at it really close with your eye, of course, always wear those safety goggles. But whenever you're in lab, but you got to be careful with these electrolytic capacitors. They will explode if you polarize them incorrectly.